Good morning, everyone. My name is Miguel Sanchez, and I work with California Control Company. We're a refrigeration company out of the San Joaquin Valley, and I've been there for 15 years. I've done a lot of, I ran jobs anyhow to install new systems, made modifications. I've worked with the engineers in our department, and through all the knowledge that I've gathered, it's put into good practice while I'm doing a mechanical integrity inspection.
Hi, my name is Michael Schreck. I'm with PSIG, also from California. I've been doing refrigeration for about 34 years, been doing mechanical integrity inspections for about 29, 30 years. Background, I've been a welder, electrician, operator, design, construct the facilities, and teach people how to run their facilities. So, well, welcome. All right, most of what you're going to see here today is a lot of pictures, and basically we want you to find out what's wrong as we're talking, okay? It's informal, nice small crowd here. If you got any questions, just stop us right in the middle of the sentence if you need to and ask the question. So let's go ahead and get into it. All right, it's called a wall of shame, and there's a reason we called it the wall of shame, because we've been to a lot of plants where they should be ashamed of the way their plants look. Sometimes we see even designs. Mechanical integrity starts with the design of the facility. Every day, doing daily rounds, doing your walkthroughs, weekly, monthly, annual inspections, runtime hour inspections on equipment, and it continues through the life of the system. What we found with the end users is sometimes they just don't see. They look at it every day, that's the way it was, and we call it tunnel vision. They should be continually looking for ways to upgrade their systems, make them safer, make them more mechanically sound. A couple things that we use to guide us with mechanical integrity. One of the documents we consider pretty much the Bible of mechanical integrity, safe operation, and that is the bulletins that are put out by IAR. They're pretty good. There's some things as end users, inspectors that we disagree with, but nobody ever agrees completely. There's a lot of things in here where they have us inspecting on a calendar basis, and we should really be doing this on a runtime basis on certain equipment, such as compressors, things that have hour meters, etc. Okay. Another thing that we use every day, or should be using every day at our plants, are daily rounds. And what should we be looking for when we do our rounds, Miguel?
When you do the rounds, as you can see here, when I'm doing an MI inspection, I always make, or a PHA or hazard review, I'm always asking if they have a daily round. Do they do their daily rounds? Do they have documentation of their daily rounds? Do they know what to look for? I was once told by a operator, he says, when I go out there, all I do is I walk through the engine room, I sniff, smell no ammonia, I listen, and I'm out of there. That's better than doing nothing. But by looking at some of this information that we have here, you can see you're talking about suction pressures. If you have a lower suction pressure, a higher suction pressure than average, and something's not working appropriately in your system, which can lead to equipment breaking down, causing somewhat of an ammonia release or an accident. We're looking at the oils. Do you have all the proper oil levels in your compressors? Do you have your discharge pressures? Once you start elevating your discharge pressure, that's where you can start getting close to possibly popping off a relief valve. Could it be that, if you have a high head pressure, your condenser may be out of water, and that's something simple you could catch while you're doing your daily rounds to avoid an ammonia release. But as far as the release popping off. Checking, as Michael said here, the hour on the compressor is very important. It'll let you know, just like changing, as we hear the 3,000 miles on our car to change the oil, it's something we need to pay attention to, hours on the equipment.
Okay. Yeah, go ahead.
The IIAR guidelines are for refrigeration systems. What about ammonia in power plants where they're using it for
19% ammonia for the NOx cut down.
Yeah.
Basically, when you're looking at the ammonia injection grids, the equipment's the same. I mean, you don't have the compressors, but where we run into most of the problems at those facilities is piping components, connections, labeling, safeties, things like that. But yeah, it's the same thought process. You're just looking at less rotating equipment.
So these guidelines would be applicable to those systems?
I would say levels and pressures at least.
Levels and pressure?
Yes. Yeah, and the visual walkthrough, noise, vibration, etc. Yeah, very good. Yeah, bottom line is runtime hours, levels, pressures, temperatures, all important information. The daily rounds aren't just to catch something today. They're also to look at trending, slow changes. We work with what we call soft problems in this industry and hard problems when it comes to mechanical things. Cars too, same thing. A hard problem, my tire's blown out, I got to get it repaired and replaced. I go down the road, my car stalls every once in a while. That's a soft problem. It starts getting worse. So we're looking at trending. We're trying to predict failures before they happen. Above and beyond the IIAR documentation and what we call the Bulletin 109 forms, which you just saw the cover of the book. I can't go through it because it's way too long. But it covers most of the things that we have to inspect. In addition to that, most people that have done mechanical integrity inspections have also come up with a little more detail, because there's a lot of things that the Bulletin 109 forms do not follow or do not have you inspect. Basically, as inspectors, we've come up, and the industry's come up with some good documentation, which we've incorporated in this, is an interview. We sit down, we talk to the operators the first day we're there. We look at their documentation. We ask them what they do and what they don't do. It gives us a feel for what they're doing on their system. And then we go for a walk with them, ask them some more questions. The first thing we look at is we look at their programs in history, their CalARPs, their mechanical integrities, their process safety information, their work orders, their documentation. And then we drill down to the facility itself and the support system for that facility, such as the engine room or compressor area and the global system. And then we go as far as drilling down to each component, and we find out what they've been doing. Have they checked motor current? Do they have local control? Is it functioning properly? Are they doing things such as vibration analysis, annual alignment on their compressors, checking end play, doing their oil analysis, and so on and so forth. It's quite extensive for each one. We actually look at their eyes. I used to be a cop, and we try to tell whether they're telling the truth or not, and find out if they're really doing what they say they're doing. And we do that for every component in the system. That's this one. The other thing we have available out there as inspectors and operators, installers, engineers, is there's a lot of documentation out there that will help us do a proper inspection. One of the biggest things we're finding recently, in recent years at doing inspections, is coming to their pressure relief valves, their safety relief valves, and the supporting piping. In the old days when we first put these systems together, we only had a few different relief valves to pick from. I'm talking about rate of relief, pounds per minute for the safeties. And those were much bigger on most vessels than what we needed. And we're finding that we can go to a much smaller relief valve, less pounds per minute released, and that allows us then to not relieve as much should we have an emergency, enough to keep the system safe, even in a situation for a fire so we don't have a blovey. But now possibly we can reduce that downwind effect affecting our neighbors, because if we're relieving the atmosphere, we can reduce the amount that's leaving the system every minute. What we're finding is relief valves that are way too big. And what that means is too many pounds per minute. What does that do? That makes the branch lines and the headers too small. They can't support those rates of relief. In this documentation, you can go through all the calculations. There's tons of them, or you can just go and get the ANSI tables, and it'll tell you the length of the pipe, how long it can be, and the pounds per minute, and what pressure it can handle for those pounds per minute. So you don't have too much pressure drop. Go ahead.
Another thing I do want to mention is it's very simple. Let's say when I'm doing my inspection, I come across relief valves that have not been replaced within the 5-year period. I always bring up and I say, look, if you're looking, and another recommendation I would make is if they're not venting accordingly, I say if you care, we can size the relief valves for you if you care to eventually vent them up to the atmosphere or put them into an absorption tank. And I recommend that when I'm careful making the recommendation better said, but I think it's a good idea with the facilities that are within the city. You have, I know, a few facilities that have high schools right behind them, markets to one side, and sizing those relief valves is an easy calculation. You multiply length by the width and by 0.5, and it'll give you the pounds per minute that's needed. When you're out there looking around, just to give you an idea, if you don't know what they look like, we like to use Hansen relief valves, and they have a green tag. The installation date tag is green. That every time I see that, I know that it's a reduced capacity. It's been sized accordingly. So it does make a difference, like Michael said. When it does pop off, you will definitely have less ammonia leaving your system than, I've seen relief valves that are sized 10 times the size of what needs to be on there. So, you release ammonia, what it should be by the pressure vessel code per the size of the vessel. Now you multiply that by 10 times, that's going to, it's a 10-time headache.
Are they cheaper this smaller?
Same price.
Same
Pretty much
price. Yeah, they're the same price.
Michael,
Yes, sir.
was this considered industry standard now to size it properly, or is the other way okay?
It always has been that way. It's in all the manufacturers recommended. You pick up a Hansen book or an RX book, they give you that calculation. That is the industry standard for them, yes. Yep, absolutely. Oop. And just real quickly, I'm not going to spend a lot of time on these two articles, but not taking care of your system or not working on your system properly can lead to a catastrophic release or an injury or fatality. This was the one that we just had down in Sanger at the winery. You hear stories, you hear 10 different versions of this, so I can't tell you exactly what happened, but the most accurate I think I've heard was a human error. They were working on a system, doing their maintenance like they should, and it resulted in a fatality. But we have lots of mechanical integrities problems out there that also lead to releases, injuries, and fatalities around the nation. All right, now I understand that many of you as regulators do not have enforcement of the general duty clause, but you still have a responsibility to consider what the general duty clause is stating. And that is that we should be in compliance with good engineering practices, and if they follow the industry standards, they follow the IAR bulletins, they'll be in pretty good shape. Comply with recognized industry standards and follow manufacturers' recommendations for use and maintenance of equipment. And most facilities are doing pretty good. Some are actually doing more than what the manufacturers recommend, and that's a good thing. Some don't follow the IAR guidelines. They have their own program. But if they can prove that they're keeping their system as safe and mechanically sound as what the guidelines are telling them to do, they're probably doing most of them or exceeding those guidelines. Some of the bulletins out there, I'm not going to go through all these, but if you go to the IAR website, they're still available. IAR is going to be taking those off their website soon. They're going to be combining those in one of their large refrigeration books, and they will not be available separate anymore. Some things that they don't copy, the IA bulletins don't cover are these three items here. Go ahead.
Testing for moisture, ammonia purity. This one here, there was a facility they were using, as far as they thought they were cutting back on cost. One facility was using farming ammonia, and carries a lot of water. And so after did a PHA, we talked about, and NMI inspection, we talked about and what they would do, they would bring in farming tanks and transfer ammonia themselves. They had no training, no PPE, and I made the recommendation, how about get properly trained or just get away from using farming ammonia. So they decided to do that. We did a pump down of the system, and when we took everything out, we guesstimate about 50 to 60 gallons of water, of moisture we pulled out of the system, causing moisture inside the system, causing corrosion, and just causing higher head pressures, more energy to keep the temperatures that they'd want, more consumption of energy, I should say. Testing the PHA water in the diffusion tanks. I like to get to facilities and I check them every 6 months when I'm doing MI inspection. It's a simple strip bar, give the customer an idea as to how their PHA is and if they had any ammonia release popping off going into the diffusion tank, it kind of gives them an idea. And brass material. Ammonia is very corrosive to any brass material. Sometimes we've seen where they use brass caps to cap a valve. We've seen, there was one instance where they had, according to the facility, they had installed a new compressor, and the compressor came with a brass, what was it, a little gate or a isolation valve, and within time it started leaking ammonia, and then they found out that, that's what the problem was. And when you see the turquoise corrosion on any kind of brass material, you know that you got ammonia being introduced to that metal. And again, it's very corrosive and it will leak.
Yeah.
Yes, sir.
You mentioned that you had a system that had 60 gallons of water out of, what do they do after that point? Do they have to flush with anything? Do they just
Anhydrator.
and everything it happens fine, or what?
There's a couple different ways to get it out. We have had sites where we've completely emptied the system because it was just so saturated, much more than that. We've had up to 5,000, 10,000 parts per million of water in their systems, and you don't want to be over 150 parts per million. What we do is we may take the whole charge out, put a fresh charge in, but typically the companies will put an anhydrator on. H.A. Phillips makes one. Other people will just simply get a nurse tank. They'll take a percentage of the ammonia out of their system, put it in a nurse tank, and allow it to bleed back into the system very slowly. The ammonia will bleed back in the system. The water will be left behind because water's heavier. Now some will go back in. So this is a continuous thing and it takes a long time. But those are the only two ways I know of getting it out.
I think we're asking whether or not you need to do testing on the pipe to make sure that there hasn't been parts of the system that has had unacceptable corrosion. So how do you make sure that the system, the integrity wasn't compromised?
Okay.
Due to the moisture?
Yeah.
That is going to be internally, and that's going to be hard to see. And I hate to say it, but if I see any outside corrosion, it's very easy to detect and perform non-destructive testing to ensure the pipe. But go ahead. I'm sorry.
IAR has no internal kind of a requirement.
Well, actually, if you suspect moisture or you
Yeah,
find
I get it.
moisture in the system and it has any age on it, typically we'll then do non-destructive testing, ultrasound, X-ray, etc. And we can test the minimum thickness of the piping that way. Unfortunately, you're only testing where you test those test points. There's no way to test the whole system. And 99% of the time, the piping rots from the outside in, not the inside out. Usually the water will be found, the degradation will be at things like orifices, restriction valves, solenoid seats, where there's a pressure drop or a smaller orifice where it's flowing through, and that's where you pick the erosion up. And the operator will then have level control problems, controlling his ammonia at each point in the system. Yeah. But there is no real, I wish we could make our systems out of glass so we could see inside. So.
You're gonna have higher operating costs too, 'cause you're-
Absolutely.
Yes.
Absolutely. Well, this particular system, what we ended up doing is we drained the entire system, sent the ammonia packing back to they were planning on using it as fertilizer, which ammonia is fertilizer, but we ended up draining the system and we ran vacuum pumps, different size vacuum pumps for 3 weeks to pull all the moisture out as best we could. Then we put anhydrous ammonia in it. And then we ran the system for a bit. Then we brought in our auto purger. We have auto purger on wheels and ran that for about 3 weeks. Now the system is running efficiently. Low head pressure. Still, I still see problems coming down the road because of the corrosion that's been going on the inside. I definitely see that coming down the road. But my thought was I made them aware, but that they were getting away from a possible ammonia release or accident by doing the same practices that they were doing as far as charging and removing the ammonia themselves. But I did mention to them that down the road you probably are going to start seeing problems that are going to start popping up just because of the corrosion that happened while the moisture was running through the system.
So on a rough basis, could you say how much more efficient the system ran after you did all that compared to before with the chlorine?
Oh,
Is there a
boy.
rough number?
It'd be hard. You have to involve engineering calculations and go back to energy consumption and all that. But I just by seeing the head pressure, I mean, it dropped. I remember it dropped maybe like 12 or 13 pounds, and they had scale buildup, which I think we have some pictures of some scale buildup on the condensers, causing it to run that much higher. And then at the end of this season, they're looking at replacing that condenser, which would drop them down even more.
Yeah, there is some equipment out there now. Technology is getting better. And a lot of our systems operate in a negative pressure. It means the suction side is in a vacuum. So if there is any leaks, we're sucking air and moisture into the system on a continual basis. Those sites are usually the most contaminated. Plants that do blast freezing, spiral freezers, the meat industry, some vegetables, fish, etc. Where we're running the, again, low side of the negative pressure now. Auto purgers get the air out for us. The newer auto purgers, though, you can get an option. You can get an anhydrator or basically a still on those. You'll get the moisture out too. And we recommend that for any new system, but it's too costly to retrofit an old system. So typically they'll use a new tank, nurse tank, or they'll rent an auto purger. Back here for the brass and incompatible materials, one thing we do carry in our back pocket when we do our mechanical integrity inspections, our walkthroughs, is a little magnet. And if we see anything that's suspect, we'll put the magnet on there. And if it doesn't stick, we have one of two things. We either have some kind of gold metal, or we've got stainless steel, which is compatible. So then we have to figure out which we have. Okay. What should we do? Should we, as end users, question or challenge IIAR? I like IIAR. They've got good guidelines, but they're asking us to do some things that in the future coming down the road that I think are unsafe. How can I say this politically correct? A lot of the people on the board sell stuff, okay? And sometimes they get a little confused about their priorities, okay? And so we need to go to the meetings. We need to get involved in the code committees, etc. Some of the other things we have to follow: ASME guidelines, ANSI ASHRAE, American National Standards Institute on Compressed Gas Association. And now let's get into the fun part. All right, everybody, you're gonna have to tell me what's wrong with these pictures as inspectors. A little humor first. The top one on the left-hand side, you probably won't see anything wrong. That's a Kentucky air conditioner where they've taken a freezer, used the cardboard box for ducting, and then they have a fan. They're blowing the cold air into the living room. Unfortunately, the condenser's still in the house, so all the heat's still staying in the house. They're not getting rid of it. The top right one, that was a mistake that a couple of meth dealers made in Florida. They stole some ammonia from a facility, and you'll see this if you see anything like this around plants. Valves that are green like this on the right, tanks, hoses, clamps, plugs or caps missing from orifices outside, such as on a high pressure receiver. Most of the time what we find is that somebody's stealing the ammonia. They use it to cook methamphetamine. Unfortunately, ammonia is a refrigerant. And when it changes from a liquid to a vapor, it takes up a lot of space. And there wasn't enough space in that propane tank. And that was in the trunk of their car, which they don't have a car anymore because it exploded too. Down on the left-hand side, that's a condenser that saw an overpressure condition. My understanding it was a combination of mechanical failure and human error. But again, if we do our mechanical integrities, if we check our safeties, if we calibrate our instrumentation, something like this should not happen because we have a lot of protection on our systems if it's functioning properly. And the other picture is just another picture of that condenser. Can anybody tell me what's wrong with this picture right here? Or what we can do to keep it safer? Come on, Don. I know you know. What was that?
Can we,
Say that again? Nope. On the left-hand side picture, those are pressure relief valves on top of a high-pressure receiver, right at face level. The outlet's right at the operator when they're filling that tank. Okay. Bottom right-hand side, that's just a condenser and evaporator in a room. So you're not doing air conditioning. When you're looking at a refrigeration system, we're talking about the condenser that's typically outside. That's where we get rid of the heat. Okay, that would be here. And then we have the evaporator where we absorb the heat into the system.
and that is, of course, as you can see, what's the issue there? That's inside of a compressor room. Kind of covered that already, I guess. That's just not properly venting. If you're standing next to that, seems to be a thermosiphon, maybe thermosiphon oil cooler.
That's correct.
That is going to spew probably oil, and oil is going to have a high concentration of ammonia, so whoever's in the area is going to get quite a shock when that pops off. As you can see on the right-hand side, we have your emergency exhaust fan. That needs to be venting straight on up to the top. As you can see, it's got a top on it, and it seems to be under a condenser. So it could hit and not go anywhere. It might circle back around to the inside vents coming into the compressor room while you're trying to hit that emergency exhaust vent to move the ammonia, and it's just going to circle around, and you're going to get yourself in trouble. So making sure that it's properly installed. The bottom left-hand corner, you can see the panel. That's a very old panel, electrical panels there. You can see it has a orange extension cord, and trace that cord, you can see that it's tied into this motor. Of course, OSHA sees that. That's quite a hefty fine. You got electrical tape on that. We're talking about a good size fine there. So, and one thing I always say, when I comb through a system, do an MI inspection, I always say everybody deserves to go home at the end of the day, to go to their family, and sometimes some of the we call them employers, don't care about the safety of the employee. And I've spoken to a lot of them while I'm doing the inspections, and in particular the one in Sanger, where the gentleman who passed away due to the ammonia release. I'll get into that a little bit later. This, you can see to the left-hand side, that's going to be your silencer for, it could be emergency refrigeration switch, it might be emergency or a high liquid level float. And to keep it silenced, it looks like they shoved a screwdriver in there to keep it quiet, kind of a hush-hush. You know, it's there because there wasn't some sort of an alert, an emergency that might be right around the corner. You can see the top right-hand corner. That valve there, it's a brand new valve. I was doing an MI inspection at this facility, and as I was walking up, the refrigeration contractor that was there, they were replacing this valve. And you can see to the right side of that valve, they got new nipple piping, new fittings, but and that's the drop leg of a accumulator inside the bunker. So that's full of ammonia, had some oil in it as well. But you can see the corrosion on that pipe nipple there. I'm surprised that nipple did not break as they're removing the pipe and putting that pipe back on there. And they didn't do anything about changing out that nipple, so now the system's in with pressure, and you got a very corroded nipple. And down at the bottom side, they're using, you can see that fancy support.
That's a 4-inch liquid line.
4-inch liquid line. That's a lot of ammonia flowing through a 4-inch liquid line. And they just put a piece of pipe, you know, sat on top of that bolt there, and that's your support. That's your handy-dandy support.
Well, on that one valve, it was the new valve that was connected to that one line. It also looks like it's cross-threaded with something.
I looked at it, and this had already, it's just the amount of the corrosion that's causing that nipple to do that. It's just eaten up, and so what I did, I thought the same thing. That's what it looked like, so I came back with a sulfur stick and I checked. There was no ammonia leak or anything.
The recommendation on that was what?
Whack it off.
Whack it off and replace the nipple. When I make the recommendation, I ensure that the pipe is safe for further use. Visually looking at that, I know that it's not. I know that it's not. So yeah, pump down, cut, replace, weld a new nipple on there, and be safe. Now, on the facility where this left picture is and the bottom right picture, this facility is old, not old, but you know, just like your home, you put in a brand new home, it starts to settle, you hear the popping, the squeaking, everything kind of settling down. This facility is settling down and moving, and the dummy leg on the bottom supporting, that's a drop leg of an accumulator, it had a weld on there. And this had moved so much that it broke that weld. It takes some good pressure to break that weld. And you can see, and when we got there, they didn't, it had been sitting like that for a while, so they thought, yeah, you know, before it completely falls off, we're going to shove that 2x4 underneath it to support it. So just, you know, systems or facilities start to settle down, and that can happen where things start moving around, and because of the dummy leg being anchored down at the bottom, it had nowhere to go. So what we did, we ended up supporting that pipe temporarily, and then came back and they ended up moving that dummy leg out and then piped it back in, or welded it back in, made it safe.
Yeah. The picture on the top right, that's the other end of that pipe that was on top of that flange. And this is, that was actually on a suction line. This is the liquid line it's supporting. It fell off a couple times, so they put a couple hose clamps around it to support it a little bit more so it wouldn't fall down. Top left-hand side, how does that valve look on that gauge? Would you want to operate that valve? Yeah, you're going to see a lot of pictures on piping, bad valves, and hopefully they'll get the pictures lights getting taken care of shortly here. But one of our most common failures, what we see out there that causes most problems, is corrosion on piping and valves, especially under insulation, where the vapor barrier has been degraded, moisture and air has gotten to that pipe, and then the corrosion starts. Every facility should have a corrosion prevention program. And that's basically random inspections every month, removing small areas of insulation where you see moisture or frost or rust coming through, etc. Penetrations through walls, ceilings, pipes that change in temperature. In refrigeration, we have certain piping that will be warm at times and cold at other times, such as hot gas defrost reliefs, condensate relief, etc. Those are areas you should pay special attention to. When you have a thermal change, that's typically where the corrosion starts on a system first. Now, if the pitting's not too bad, we'll clean it to bare metal, paint it, recover it with insulation if it's insulated. But if it's questionable, if the pitting's too deep, then we'll bring in non-destructive testing. We do not use NDT in this industry on all the piping and vessels that we work with because, again, ammonia facilities rot from the outside in, not the inside out. When we see a suspect plant, though, then we'll recommend the additional non-destructive testing. Typically, the money's better well spent repairing what you find visually and repairing the insulation. If you see rust coming through like this, through piping, through coatings on piping, insulation on piping, you know you have a corrosion going on underneath. This happens, yeah, you're not even going to see this one. This is a picture of a component with the whole side blown right out, and it's called hydrostatic expansion. And this is where they were not doing correct maintenance on a liquid line, and they installed an additional valve that shouldn't have been in that line. It was a check valve. Yeah, it should not have been in there. Hydrostatic expansion occurred, and it ruptured the side of the equipment right out.
This particular picture was taken not too long ago. And last Tuesday, some of our construction crews are out there replacing this, and I made this recommendation 2 years ago at this facility, and they're telling me they did not have the funds to look into replacing pipe. Half-inch nipple that's supporting, there we go. Good job, Mike.
Had to find it sooner or later.
That's a half-inch nipple supporting that three-way valve. And the emergency is at maybe about 5 feet, so it's not properly terminated, but residential area, down about a quarter of a mile, you got a school in the direction of prevailing winds. Well, this recommendation was made, and finally, 2 years ago, and finally they called me up and said, hey, can you come in and take a look at this? So we took a crew in there. We were replacing the relief valves as well, sized them up properly. And when our guy was removing, we're going to reuse that same three-way valve, or the manifold for the relief valves, as they were put a pipe wrench to remove the pipe nipple going into the three-way valve right at the threads, snapped. And this system, I feel like it was a matter of days before they had a huge ammonia release. And again, a pipe nipple, that's one of the weakest points in the system. You remove material off of Schedule 80 pipe. This happened to be a half-inch. You remove the material off of this pipe to make the male threads. So that's a weak point. So I always look to make sure that it's properly supported. And so this one here, like I said, once I showed the owner, he grabbed his head and says, oh my goodness. He didn't realize how close he was to having a big release. This one here, this one is...
Ask them what's wrong with that one. See if they can figure that one out.
Tell me, yeah, that's good.
Yep.
What's wrong with this one here?
Yep.
Plug. And there's one more thing. Look closely, one more thing. Yeah, isolation valve, actually there's another thing. You see that big isolation valve coming off, that's a condenser, coming off the condenser. That relief valve, there's 2 more condensers there. And that relief valve, they didn't want to replace them. It was past their 5-year replacement period. And this facility right next door, I can throw a rock from this facility and hit a supermarket that's right next to it. Condensers have them right up on the isolation point, and they're there to relieve the condenser. This one is on the opposite side. The reason why is they ran out of room. From the face of the condenser to the wall, they had no room. On the other 2 condensers, there must have been probably about a foot of space, so they had room for the relief valves, but this is on the opposite side. And so once I made the recommendation, talked to the plant manager, he just says, wow, had no idea.
Yeah, usually when you see relief valves plugged, it means they've been having a problem.
Yeah.
A couple of years ago down in Houston, Texas, at a Goodyear plant, they had a heat exchanger explode, shell and tube, and kill a lady. And that was because the engineers at that plant had plugged the relief valves. The CSB interviewed them to find out why the relief valves are plugged. They said, well, every time we pressure wash those things, it pops off the relief, so we plugged them. You can't fix stupid. You just can't. Okay. Another problem we're having out there, or challenge I should say, is with new evaporative condensers, or some people call them cooling towers. That's your piece of machinery outside that has the water and the air going through it to remove the heat. We're having a terrible problem with white rust. And not only at startup, but the white rust is coming back again years later. The sites should be looking at their condensers almost every month. Well, actually, they should every month. We have to passivate the equipment when we put it in, or we used to be able to use chromates in the water. We can't use that anymore because it's a heavy metal. And so what happens is at startup, the zinc comes out of the galvanizing and then reattaches itself. It's looking for carbon steel. And it will quickly eat through the galvanizing. Then they have no protective coating for their tubes anymore in their condensers. And those are only 40 thousandths thick approximately from the factory. So it is a weak point for us. A condenser can be totally destroyed in a matter of a few years, when we should get 25 to 40 years out of a condenser if it's depending on our water quality, how well we do the chemical treatment, and how well we perform our maintenance. But we are finding a lot of that. So make sure that your end users are passivating their condensers and then looking at them from month to month, because that passivation layer can wear out over time. And they'll have to treat it with something like molybdate or another protective coating that's applied in the chemical treatment. On the left-hand side here, you've got a new galvanized coupon. We put these in condensers when we start our condensers up, because these coupons will show us the white rust before the condenser actually does. The center one is a coupon that's been attacked by white rust. Now, this is very aggressive here. Typically when it starts off, it just looks like a snowflake or two, and then it accelerates. And then the one on the right has been one that's been passivated with a protective coating to hold that zinc in. Otherwise, if you look up here at the right-hand side, this condenser right here was only 12 years old, maybe 14, 12 or 14 years old, and it's completely rusted. Okay. Other things that you should look for naturally is just simple things. Corrosion on the outside of pipings. One of the biggest areas we find corrosion is by our condensers. We treat our condenser water with chemicals, and then sometimes we have some overspray and that lands on the piping. And this one on the left-hand side top there is one that's running along the top of a condenser. And then, of course, the one on the bottom left, that's simple. It's open electrical. We find that all the time. And on the right-hand side, you'll see oil all over an ammonia valve, a solenoid valve and strainer. What is that oil telling you? Yeah, you've had a leak somewhere at one time, you're leaking now, or you're going to leak again. Lots of times the oil will come out first before the ammonia does. And it'll be nice enough sometimes to seal that gap up for us enough that we don't smell it. And then someday it's going to let loose. This particular site, I found this one at. A year later, I came back to do emergency response training, and our drill was to go up on the roof to isolate these valves. We went up there, and that valve was still like that, and now it was dripping liquid ammonia on the roof while we were there. So we had a real emergency response. It was a good training exercise, but not something I want to do all the time. The other thing we're running into is people aren't using engineers to design their structures, to design their supports for their equipment. That white line you see there is a piece of string. I've got it attached to one end of one condenser and it goes to the other end of another condenser. This particular one I was called to look at, it was up in Minnesota, and they busted off a 1/2 inch nipple for an auto purger on the condenser outlet, and they had a major release because of that. And that's because they didn't support the condenser properly in the center, and it actually sagged about 1.5 inches in the center. Anybody tell me what's wrong with this picture? What kind of switches stop? I wouldn't know because it's not labeled. And that's another thing we run into out there. And we don't just look at mechanical stuff when we do an inspection. Didn't have a spare. Screwdriver's good enough. This picture is actually taken from by Bradley Miller. He's with EPA out of Region 6. He gave it to me. Another thing when you're out there walking the systems is look at any point where there could be any gaskets or flanges bolted together. And like that solenoid I showed you up on the roof, look for oil. Look for white powder. That tells you that you've had a problem or you're going to have a problem. Now, it's not unusual for a system to have a little trace of oil here and there. Okay, but if you go in a system and you see oil all over the place, you can pretty much assume that they're not maintaining their system. This is an example of one of the relief nipples that broke. It was rattling when I went to inspect it, pulled on it, and it wasn't even connected anymore. We are having a problem with the nipples that support the relief valves, support the three-way valves, that support that house the relief valves, and usually on screw compressors. We get a high-frequency vibration on screws. Typically, that's because what Miguel said here, the building's settling. The building starts to settle, the pipes start to hang lower, and they push down, usually the suction line on an ammonia compressor, and that extra weight causes a high-frequency vibration. And those compressors typically will crack lines, crack nipples. You'll see oil leaks all over these compressors. The valve handles fall off. They have seal and bearing problems, etc. And that's as the building gets older and it starts to settle. Just an example here. This is one. This was up at Columbus Distributing in South San Francisco. You may have heard about the bad release that they had a couple of years ago. Gassed out. What is it? Gentrek or Genentrek, something like that next door. They had a pinhole leak in a pipe, so we did the inspection on it, found the bad piping. They replaced it. But I also identified a pressure switch that had a brass fitting in it when I was there. I gave them till the weekend to replace it. They didn't replace it. Guess which fitting let loose and gassed out Gentrek about 6 months later. That was that fitting that we found.
I have a question about these fittings. Since it's for ammonia, and we know you can't use brass for ammonia, why do they make the fittings?
That fit? Yeah.
Why do they make fittings?
People have actually recommended that we use a different type of thread pitch or something like that so they can't be used. Well, I don't know. Too expensive, I guess. Yeah, too much of a challenge. Usually, it is the most common place we find a brass fitting is somebody's gone in there with a test meter. There's certain fittings we can't get in for some of these ports except in brass, and they'll use it for testing purposes, but then they'll forget and they'll leave it in. South San Francisco, Columbus Distributing, they had a bigger challenge. That plant has both Freon, R22, and ammonia. So they have a system that is compatible with brass, and then they have an ammonia system both in the same engine room, redundant refrigeration systems. And one guy just grabbed the wrong fitting, out of the wrong can, and used it in the wrong place.
This year is the emergency control box. Depending on the year that the facility was built, you needed to install an emergency control box. Emergency control box needed to be labeled emergency control box up in the front. On the inside, this one is missing the labeling as far as the instructions as how to operate the valves. The valves are labeled, valves 1, 2, and 3. Valve 1 being the this is used also to release and dump all the ammonia out of the system in case of an emergency. Very rarely will this be used, but it's there for a reason. Valve number 1 is your high pressure side, usually relieving all the pressure from the high pressure receiver, which is your high side. Valve number 2 being your low side, which relieves the low side gas vapors. And then you got your equalizer line, the one up in the middle, tying from the high side to the low side. By fire code, you need to be able to vent from the high side to the low side. Now that could be key. Let's say somebody punctures out in the plant, somebody punctures a high pressure liquid line. To drop down the pressure to release less ammonia, you can dump the high to the low to equalize the pressures. You could be going from 110, 130 down to 30 psi. You equalize that, you're having less ammonia being spewed out through whatever the leak may be on the plant. This one here in particular, I opened it up and I, realized that, of course, all the proper labeling was not there. But when I looked, if you look carefully, it's hard to tell in this picture, but the equalizer line does not tie from the high side to the low side. It has a 90 and it turned back inside to the compressor room. And I got into the compressor room, I'm tracing that line, it was capped off. So why it was capped off, I don't know. And I could tell the cap is different age-wise from the pipe. So at some point that was capped off. So that's one important thing to keep an eye out, to make sure that high side to low side equalizer is connected.
Yeah, you got to have, in the old days, up until the code just changed, you had to have a manual high to low, okay? Now that's done automatically. The new code is we have a pressure transducer and we operate an automatic valve. Pressure gets too high on the high side, we dump it to the low side. Yeah, so now that's done automatically. And these are not required by code anymore, the emergency or fireman's control box.
Michael, was that hand feel on that one valve, was that brass? Is that why it's that color?
No, it was just painted. That's just the color of that was painted now, but it wasn't a brass hand wheel. This here, you can tell this is a high pressure receiver and it's 100% full of liquid. And
Was the system operated?
the system was operating, and now, as Mike said, you need to have room for expansion. Gas, liquid will boil into a vapor and it needs more room, it occupies more room. So by pressure vessel code, you should not have more than 85% of your vessels full of liquid. Well, this is 100% full. And at this particular facility, as Mike mentioned earlier, the death in Sanger at this ammonia winery, ammonia facility, it's a winery. And when I went in, I did the MI inspection about a month and a half after the death had occurred. And I'm walking around, I'm talking to, it's for one, it's kind of weird to see where you see, the individual who passed away, what he was doing, where he was going. And I'll take a quick second to share a quick story with you on that, how the main operator there tells me that one of the other operators during the night shift came in and they had a chiller that was icing up. They used their hot gas defrost to defrost the chiller. So next to the valve here going into the chiller, 6 to 8 inches away was the oil drain valve. So as he reached in, he was coming in to grab the isolation valve to open it up to manually defrost the chiller. Somebody called him. The guy turns away, and when he turned away for a split second, came back and he grabbed the oil drain valve. And that oil drain valve was not plugged. And this facility, before they were making up their own CalR program, if you will. They said they were, and really they weren't. And that valve was not plugged, so when the guy, the operator opens up the valve, ammonia spews, he runs away, evacuate. Right behind him, about 15 feet behind him, is a door to the gentleman's restroom. Well, an opening that has no door. There was an individual, the guy who passed away was inside using the restroom, and as the ammonia filled up in the area, the guy comes out running, and or comes out with his eyes closed. The camera is 20 feet away recording everything, surveillance camera. So the guy comes out filling, he has his eyes closed and he's touching the walls to the right-hand side, and this guy had no training whatsoever, had no idea what ammonia was, he just knew it was, there was ammonia in the system, but had no idea, no training whatsoever in regards to ammonia. So when he didn't know how to react to it, he just came out and he panicked, and he went filling the walls to the right-hand side. And there was no training, documentation whatsoever. So, and my thought was this gentleman knew, if he wouldn't had some sort of training, he would have came out filling to the left-hand side. He would have made it to, he would have been here today. It was a free path to open area where the big driveway and a lot of air flowing through that area. And the sad part about this is the guy who opened up the valve and the guy who passed away were cousins. So,
Yeah.
sad. And that is testimony from an operator that was there the night of the accident. So I feel pretty good about telling that story. What we got here, same facility. It's hard to tell if you can tell. This is a relief valve, of course, and you can't really see the pressure rating on there, but this is a 250 pressure rating on this relief valve. For one, the installation tag is not punched. You got the the date of installation. You flip it around, and it tells you by when you need to replace it. Within the 5-year period. But this particular relief valve sits on a chiller, and the maximum allowable working pressure, which is on the nameplate of that vessel, is 225, and they're overseeding that by adding 250 psi relief valves on there. That is not. That relief valve needs to be 225 or less. It cannot exceed the maximum allowable working pressure on that chiller. So that's one thing I always keep an eye out, because I've heard that
That's not the one that had the propane tank for high pressure receiver, was it?
That's no.
Okay.
But
No
that is
kidding.
what can happen.
Yep. Compatible. Well, actually, they've been there for 20 years, so they must be compatible, but they weren't designed for ammonia refrigeration systems. One thing I just, as an end user that I have been in the past, and an operator, a lot of times our nameplates will get painted over, they'll be insulated over, they fall off, etc. I was also an inspector in the state of Wisconsin. If the thing has been there for 10, 15, 20 years, and I don't see any pitting or very little pitting or something, I'm not going to condemn that vessel. It's been there, it's proven its life. But they should have legible nameplates, and they should have, and in this day and age on newer facilities, the backup U1 form, which basically is the birth certificate for the vessel on site. This happens to be a pressure relief valve that's on top of a nurse tank, just relieving directly to atmosphere about 3-4 feet off the ground. When you're out there walking the plants, everybody, use all your senses. Look, listen to things, touch things, always use your nose. A little odor isn't a bad thing. If you had a perfect system and it was newer equipment, you might not get any odor. But there are some places you are going to pick up some odor, such as shaft seals at compressors, ammonia pumps, you might get a little bit of odor. Seals weep a little bit, and it's just a normal thing in our industry. But it shouldn't be to the point where the site's complaining. It shouldn't be anything that should be more than just a slight irritation to you. Think about what you're looking at, get together with the site, and come up with a plan. It seems like they walk through the plants every day, they do daily rounds, but they keep their heads in the sand. So all too often we have operators that write numbers down on a daily round sheets, but they don't use them, they don't apply them, they don't even know what they mean. So training is a big part of mechanical integrity. If they don't know what they're looking at, they're not going to be able to keep their systems mechanically sound. They should have documentation of the minimal requirements, which is SOPs, overview of the system, basic refrigeration, etc. This is an example of a nameplate that was missing on a vessel. Vessel's been there forever. We took some of the insulation off and it was fine. And the local AA was okay with that because the vessel's been in there for 20-some years. You see any green on a system out there? It's telling you something, okay? And then, of course, corrosion. Excessive ice buildup can cause small lines to break. Go.
Corrosion and erosion. And yeah, you see that bottom right-hand gauge. Anybody can tell me what's wrong with that gauge? Yeah, if you have a 300 psi relief valve, it's about to pop off. If it hasn't already. If you have a 250, it's popped off. Look at that pressure. That's right at around 300.
Yeah, about 295. The reason that's like that is because they trapped liquid in that line, and they had hydrostatic expansion. There was 30-some gauges like this in that facility. And that's because the operator turned the wrong valve and didn't relieve, didn't bleed off the liquid before you isolated that location.
They trap it, and once the liquid is trapped, a little bit of heat is added. Again, it expands, and it's going to find its weakest point and make its way out and cause a stink about it. Coils, this is a spiral fin coil, the picture to the left-hand side, top left-hand side. Corrosion, SO2 gas eats up away at everything. Could be bad water as well. I believe this particular facility was using ditch water to defrost.
Yeah, when you get into wineries, when you get into dairies that are using saltwater brine or salt water in their production, When you get into banana rooms, where we have banana ripening rooms, then they're using ethylene. All those things cause corrosion to the air units. And so they have to inspect those on a regular basis. A lot of people think that these coils are going to be good for 25 to 40 years. In those corrosive atmospheres, they won't last that long. So they need a little more attention than, say, a cold storage warehouse or something that doesn't use those chemicals. We even run into this in production facilities where they're using sodium hypochlorite or other things to clean their floors, CIP chemicals, etc. And that will go to the air intakes, get to the coils, and accelerate the corrosion.
Yeah, there was a facility where they're using, I think it was chlorine, and the coils were 12 years old, and they needed to be replaced. Not good.
You know,
Yes.
a lot of it depends on where their injection points are.
Yep.
SO2.
That's correct.
Everyone I've seen where they have the injections below the coils, like that.
Yep.
Yeah.
Worse. Put it above it, maybe 3 or 4 feet above it, just
Yeah, and the other thing is we recommend that plants that are using chlorine or bleach or whatever it is to clean their plants, that they turn their air units off while they're doing the cleaning until they do their wash down to get rid of most of the airborne material.
Yeah, and you can see more corrosion on the right-hand side. If you don't know that there, I'm sorry, if you didn't, I should be looking at you while I'm talking, but to the right-hand side there, we see that there's about 70 feet of pipe that's not supported per NCAR 2 and IAR. There's specs on feet per size of pipe that need to be supported. This facility, there was you could see the all-thread hanging from the ceiling on the sides of the pipe, but the supporting across that was from one all-thread to the other is completely corroded away. It's no longer there. And again, there's about 70 feet of pipe there. For instance, a half-inch, 3/4, 1-inch pipe should be supported no more than about 7 to 8 feet. This again is 70 feet. Down on the left-hand corner, erosion. This facility here is a very old facility. That is a supporting the coil that's above it. And you can see there's about an 1.5 inch gap from the bottom there. This is a very old facility. This is one of those facilities where they still have, they used to use they'd bring the tons of ice, drop them in the bunkers, and that's what the refrigeration was. Circulate the air and cool down the air. Very old facility. Erosion the water draining has eroded away the cement. You have some rocks there, and that supports not supporting anything anymore. Top left-hand side. What is that? Who knows what that is?
You know what piece of equipment that might be?
That is a plate fin ceiling suspended coil. Now, what cools down, the air that flows through the coil fins is where the cooling process is going on through that coil. This, it's just dirt buildup. It's a wall of dirt buildup, and there's no refrigeration going on through that coil.
I want to give you more examples of what you should be looking for. So we're just going to go through the pictures rapidly because we're almost out of time. We need about 15 minutes for questions. The one on the top left, that round disc is actually supposed to be welded into that beam, and it's actually pulled back completely out. The one on the right, top right, over here, does anybody know what kind of piping this is? Is that carbon steel? Is that galvanized?
Stainless steel, maybe?
What do you think those elbows are? Yeah, they're galvanized. That's on an oil drain. Even though it's after the oil drain valve, guys will use just about anything on that. It's a good practice not to be using any incompatible materials at all. Okay? There's no pressure. There should be no ammonia on that, except for when you're draining oil. But still, it's incompatible. Bottom left, I think that's self-explanatory. We have relief valves that are plugged in. We find this more often, more and more often. And then we have here, this particular facility. Should have probably known they've been leaking ammonia for a while. It's taken the paint right off, etc. Signs of oil again dripping. Go ahead.
More corrosion going on here. Again, this is inside of a bunker. A bunker is, I'm sure, the least visited area of an ammonia system. We get in there and find a lot of the corrosion falling off of supports. You can see to the left-hand side, we got a carbon steel support that is supporting the ammonia line. or I'm sorry, that's not the ammonia, that's a defrost water line, but that corrosion is falling down on the coil, causing electrolysis. Any metal contact with aluminum will cause electrolysis, cause it to corrode, weaken, and cause an ammonia leak to develop. Again, on the right-hand side, you got a carbon steel bolt corroding. You can see where it's dripping onto that pipe. That bolt's not changed. If it doesn't corrode fast, I should say, it's going to cause an ammonia leak on that ammonia pipe there that you see. We got the, again, Mike said this a couple of times, but what's going on with the top left picture there? What's the eye catcher there?
What does that tell you? A couple different things. What was that, Don?
Good.
Yeah, possibly water sitting on that. And where's that water going to be sitting? Also on top of that relief valve disc where that spring is. That also could tell you two other things. There's three possibilities for that. What was that? It's got a gold seat, brass, copper.
Galvanized fittings, yes.
Yep, galvanized fitting with the wrong type of seat. Yep, very good. Okay, and what else? Ammonia has seen that, huh? Is that ammonia on the inlet or the outlet where that green is? It's on the outlet, which means ammonia has passed through that, or, as Don said, there's moisture. What we like to do when we install relief valves is we like to put a little drop leg here, okay? Kind of like what you would put on your gas line to your furnace, so you can catch all the crap down in the bottom, etc. Also, if we have a little bit of moisture that gets in it, it'll get down in that little drop. It won't sit on the relief valves themselves. Yep. Very good.
To the right-hand side there, again, that if I go and I crack open that valve, as you can see, it's not plugged. What's going to come out of there? Ammonia is going to come out of there. Valves need to be plugged, capped, to avoid an inadvertent ammonia release.
Yeah, if you're not working on it, it needs to be plugged and capped.
To the bottom left-hand side, what's the issue there? It's probably hard for you to tell, but that is a sight glass. That is a very scary sight glass telling you the ammonia level inside of the high pressure receiver. That one was broken. And the high pressure receiver had ammonia. The little valves were isolated, but they didn't do anything about replacing it. It was broken, and I always make a recommendation when I see this to look into putting a sturdy bullseye column or just to remove. That's just thin glass. I knew of a story of a gentleman that was cleaning the engine room. He's sweeping away. When he went back with his broom, boom, he pops it, causing an ammonia release.
Yeah, it's real thin. Basically, this is one of those things where if you see this type of sight glass, the top section there, in a facility, recommend that they replace it with armored bullseyes or armored plate glass. There's little grommets here that are used to secure that, seal that to that tube, and when you get small leaks, they'll just tighten those up. Well, they tighten them up too many times, they crack the glass. Okay?
Mike, can you point out that little 1/4-inch drain valve down at the bottom?
This one right here?
That little 1/4-inch drain valve is an easy, I've replaced them myself, where it's a 1/4-inch nipple and the nipple's bent because somebody stepped on it, used it as a ladder to reach up and do something up here. That valve should always be protected. It should always have some sort of a guard, because once that valve breaks, you're going to have a heck of a time trying to get back under there and isolating. You can see the isolation valve on the bottom. You're going to have a hard time isolating that valve. I mean, that's going to be a done and run type situation. You get out of there as fast as you can.
How many of you are gardeners? How many of you are gardeners around the house? If it's green, I can kill it. I'm not a gardener, but that's the top of a condenser right there with a tree growing out of it. That tells you that the guys haven't been up there looking at those condensers. We have a terrible problem in this industry with our water treatment people. They test the pH, the conductivity, they look at the bleed, they look at the cycles of concentration, etc. And they're the ones that are selling you the chemical to take care of your condensers, and they never go up there and inspect the condensers. A good water treatment guy will go up there. All the sites should be following their water treatment guys around to make sure they're actually inspecting the condensers to see what's going on.
This particular condenser has been replaced. It had it looked like a white sheet of paper going across it with scale buildup, and the chemical treatment gentleman was fired from this facility. As a matter of fact, fired from the company is what I heard, because he was not, as Michael said, he was not doing his job. Funky ammonia diffusion box. I'm sorry, fire dump box, emergency control box. Went over there as I was going to look. I opened up the door, boom, it fell down. No labeling.
No SOP?
No SOP, no instructions, just And the good thing about this is that this place has now been condemned, and it's been closed down. I'll say that.
Yeah, we're showing you a lot of bad pictures, but in all my years of doing this, I've only had to condemn one facility, and it is out of business. They've tore all the equipment out. The old Watsonville canning down, which became terminal freezers. It wouldn't pass seismic or anything, but yeah. Usually we can repair these reasonably.
And what happened at this facility, I'll mention real quick, mine did mention harmonic waves off the compressors. What happened was a compressor, the weight of the suction line was coming down, and it broke the bolts. The weight of the building came down and causing the bolts to break, causing a large ammonia release. Over 8,000 pounds of ammonia was released. And after that incident, you know, there was absolutely no compliance going on with that facility, so they were terminated. To the left-hand side, what do we see there? Top left-hand side.
Anybody know what kind of valve that is? That's a pressure relief valve.
Right at about chest level. So I hate to be walking by there when that thing pops off. You can see the bottom left-hand, pretty obvious. You got a hole there. And across the street of this facility, there's about an eightplex. Little kids running around, playing right across the street.
That's a pretty small vent diameter.
Yeah, that's probably not any good. If you looked at the ASHRAE table that I showed you earlier, I'll give you an example. A 49 pound per minute relief valve. If it has a 3/4 inch pipe, that 3/4 inch, and 250 pounds, that 3/4 inch pipe's good for a -6 inches in length. And this one right here is probably a 1/2 or 3/4. It's probably too small. I can't say that for sure because I don't know what it's connected to, but probably.
So the picture to the right-hand side, what's the issue there? There used to be a compressor sitting there. You got the high stage discharge and you got the suction side. The isolation valve groups. There's no flange, and the system is operating. There's about 4 compressors right next to it. The condensers, there's 2 condensers right next door, or right next to them, and you just go over there and you crack that valve open, you're releasing ammonia. High pressure liquid line, I mean, it's obvious, it's cracked. It's hard to see for you there, but there is a crack on the high pressure liquid line going through that pipe there, and that pipe has been replaced. It has been replaced. No ultrasonic thickness testing was done. I mean, it's a pretty, you save the money, as Mike was saying. It's just, if it's feasible, don't do non-destructive testing, but just replace the pipe. Spend the money on replacing the pipe.
Yeah.
Make it safe.
We've done hundreds and hundreds and hundreds of mechanical interior inspections, and rarely do we ever use NDT. Because almost always, 99.9% of the time, we can find the problems by looking on the outside. There is times when we do it, when we have a system that shows the signs where it has to be done, vessels, etc. But typically, they spend the money on replacing the pipe and insulation. Most of your facilities think their insulation is good for the life of the system. If you go to an insulation manufacturer, they will tell you the life expectancy of insulation is somewhere between 3 and 8 years. And that's if the vapor barrier is kept intact, people don't walk on it, and it was applied properly, which we didn't do at most sites. We didn't apply the insulation properly up until the late 90s.
I do find a lot of vapor barrier missing. The vapor barrier is completely gone. You got just the polyurethane insulation with a PVC or aluminum jacking, but there's no vapor barrier. So
Yeah.
keep an eye on that, accelerating corrosion.
Bottom right-hand side there, how many times do you think that plant has done valve maintenance? Zero. The 2 biggest issues we have out there is the piping and insulation, and the other one is valve maintenance. I teach emergency response, and I'll tell you what, we've had a number of times when firemen have tried to turn a valve and they can't turn it. They need to backseat that valve, clean that stem up, loosen the packing nut, lube that up, lube everything up, run it in, run it out. Now, IAR says that we should be doing that twice a year. That is overkill. It's a financial burden on the facilities. The valves don't go bad in 6 months. Once every 3 years in non-corrosive areas is more than enough. And then once a year, maybe, if we're around condensers where there's overspray or there's some corrosion problems, like in a salt brine, chiller room, etc. But as far as that, that's never been done.
And if the valve is seized up, when you need it to isolate, you're not going to be able to, it's not going to be functional. You're going to have to do a large pump down and replace the pipe.
Yes. And what do you think would happen if they turn that valve right now to the valve packing?
All the valve packing's going to get affected by the pain, that's just going to leak from there.
Yeah, and now you got to go down to the next valve, isolate that one hopefully, and pump that down and fix it. That's correct. Obvious here, just corrosion.
Corrosion.
The other thing we need to do when we're out there is we need to use our ears and we need to listen to our equipment. We need to listen for abnormal noises. You can go to the next one. Vibration analysis, always good tool, combined with other testing. I'm going to ask, there's a gentleman here named Don Tragathon. Can you tell me about this? I've never gotten a story on this one.
Oh, okay. That's a 500 horse motor, drives a compressor. The rotating member that you see at the bottom of the screen, there's got a shaft that turns 90 degrees. That's an abnormal condition. The plant was operating, and when they realized they had a problem, is when they had to come put the fire out underneath the pallet of produce because the bearing finally failed and threw red hot bearings around the yard. And basically, it was one of those things that they just started and they ran it, and when things don't make noise, that's when they get attention.
Okay.
And so here is a lubrication problem on the bearing, and over time, it started to seize up, and it heated that shaft up so much that when it finally let loose at its coupling, you can see that the laws of inertia are correct. It will throw it a 90-degree to its rotation.
That's the first time I've seen a motor shaft in refrigeration turn like that. That bearing had to be making noise for a long time. That's why we do bearing analysis. That's why we do our annual inspections, and that's why we use our ears as we walk through the plant.
That happened in about 1991, and I'm happy to say it's not the same mode of operation nowadays, but at any rate, it can happen.
Yes.
So no ammonia release associated with this. No big emergency response. Definitely an inconvenience to that user because 500 horsepower supplies a lot of refrigeration that they need.
Absolutely.
Yeah, production's down. Yeah, I used to say, and I worked for a Miracle Corporation for 15 years, and we got sold out and they started cutting our budgets. And I basically said, if you think maintenance and safety costs you a lot of money, try paying for an accident or a big release. It's a whole lot more, yeah, in the long run. Go ahead. Feel, again, walk around. Is it cold? Is it warm? Should it be cold or warm? Is it vibrating? Again, vibration analysis. And of course, you're always using your nose when you're out there. Always smelling for ammonia.
And if you can withstand the level of ammonia, it's safe. It's not a carcinogen, so ammonia's not going to cause cancer, so you'll be fine. Obvious, right?
Does anybody know what we're doing there and what's making that smoke? Yeah, using a sulfur stick, looking for leaks. And then finally, when we find all this stuff wrong, what are we doing as end users? I don't have the budget. I don't have the time. That's the way we always did it. Second shift will take care of it. We don't have the parts. Production is down. Later, okay? It's not my job. Next year, or I won't make my bonus. It seems like the last place people spend money is on the refrigeration. They'll spend money on production. They'll buy new office equipment. But it seems like the last place a production facility wants to spend money is on that refrigeration. As long as it's cold, hey, leave it alone. And we see that all the time. The other thing is when you're out there walking the plants, look at security too. Everybody should have a meet and greet policy. The ammonia theft is just getting out of hand, and it's causing a lot of releases out there. We've had kids drill into pipes with cordless drills. We've had people leave valves open, etc.
Or we've seen pictures where they come in with a 5-gallon bucket, just an open 5-gallon bucket, wanting to steal the ammonia, and you could see where they had a hammer and they broke the valve, and you can see as the trail goes where they're leaving their jacket and their shirt and their pants and underwear because ammonia got all over them. They're not very smart. You can see this poor lady here, methamphetamine user, how she looked in '98 and how she looked in 2002. So methamphetamine is not good for you.
All of you understand that they are using it to cook meth, right? The ammonia? Yeah. Yeah. You can go past this. Let's get into the pictures. Keep going. Too many tools. Keep going. All right, back up one. I'm going to take this. Another thing that a big failure in our industry is to annually test our safeties and calibrate our safeties and our controls. And the same goes when they're starting a plant or after modifying a plant. They should have a checklist, and they should be checking all their safeties. If nothing else, they should be checking their high-level cutouts, and typically it's a float, for their compressors to protect the compressors, and they should be checking their high discharge pressure cutouts. So you can't have an overpressure condition. We should never lift a relief valve. Okay, we have other controls in our systems to protect us, high pressure cutouts, etc. The relief valve is the final backup. If a plant is lifting relief valves, they're not testing their safeties.
Again, it's an element of the RMP, PSM,
Yep.
your PSSR, pre-startup safety review.
We'll just go through these real quickly. We only got about 5 minutes left. I'm just going to show you some pictures. Here's a sign of vapor breakthrough where the insulators did not use enough thickness when they put the insulation on. This is at an engine room in Tulare County that they're going to fix this. I can say that because Don's a fair CUPA. These are the exhaust vents for the engine room. Which way are they pointing? Pointing down. And look at the stairs going up to the condenser. Any odor at all comes right out those fans. That's their continuous ventilation, and it's part of their emergency ventilation. It's just going to blow it down, and directly across from that is the receiving dock for rail. And so it's going to get blown right into that building. I think this is pretty obvious. We shouldn't have ice buildup like this on air units or any type of evaporator. Right here, we have a packing nut that's just about gone. This plant is only 7 years old. And the contractor installed all the valves outside pointing upward, stems pointing up. And now the rain and the moisture just sits on that valve, and if it sweats, that moisture sits on it too. Typically, we installed them sideways, so we don't have this problem. Can anybody tell me, now this isn't a mechanical thing, this is a safety, this is something that's helps us in emergency response, and it's a code requirement. There's something missing here. Say that again? Yeah, pipe labeling. Every change in direction, every 30 feet, every penetration on each side of the wall or the roof. As an emergency responder, I want to know what's in that pipe. I want to know what pressure it is, and I want to know where it's coming from. And that's what the industry standard has done. They've come up with decent pipe labels for us that give us that information. Dirty coils, things you should look support. This particular site clamped one pipe to the other one, and the rope was the final support. This picture's actually upside down. Intakes for motors. We're having a terrible problem in our industry with some new equipment that we're purchasing. That is variable speed drive starters and motors. We have to cool those. And we're pulling in outside air to do that, and we're not filtering that air. And that's filling our starters up with dust. We've had dust explosions where we've had phase-to-phase and phased-ground faults. We've had, arc flashes and then had dust explosions. We've had motors start on fire because they're completely full of dust. A lot of the dust we work around our production facilities is combustible. Okay? Most cardboard, wood products, any food products like flour and sugar are all combustible, and they're going into our electrical components, and then we're getting a short and an explosion. Relief valves at face level going to atmosphere. Can anybody tell me what's wrong with this oil pot? Supported by wood. There's a wood block underneath an angle iron. But it's right here. This is our normal oil drain. And there's no threads or anything on it. It's just a pipe that's cut off, so you have no way of plugging or capping that. The other thing is, real quickly, every piece of equipment we have out there is supposed to have a unique identifier per IIAR. So this is an oil pot. It should say oil pot number 1 or say OP-1 something. Okay? If I got a fireman and I want to send them in there on an emergency, I want to be able to tell them what to look for. Otherwise, I'm going to have to tell them, that little blue thing, much better if you got an identifier on it. I'll let you take a couple. Brass and galvanize.
Yeah, you can see there the brass valve here, galvanized T there.
You can just click on that.
Again, supporting, this is supporting
Condenser drain line.
condenser drain. You got the spacing here, corrosion going on as well.
This right here is actually a 3/4 inch valve. It's a Weldon valve made by Hanson. Condemned it that day. 2 weeks later, they got a pinhole right in the housing itself. Okay? And I think we're out of time. All we have to do, we have time for questions.
You got a couple minutes. Questions, please. Go
Go
ahead.
ahead in the back.
Can you kind of go over some good elements, corrosion protection program for insulated
The question is going over corrosion elements.
Yeah, for insulated piping. I'm always a little at a loss. I know you say where the water is,
Yeah, if you see now,
what's like a time frame of removing the insulation?
well, they should be doing sampling every year. Not the first 5 years a plant is after built. You know, you're probably going to have nothing. I've never heard of having a problem. But every year they should be looking at suspect areas: drop legs, low spots, penetrations through walls, pipes that change temperature. So
You just take out a chunk.
just what we do is go ahead and make a few clicks there. I probably got one.
One thing, if you see the corrosion outside,
There you go.
yeah, there you go. If you got corrosion outside of the insulation, you know it's bad on the inside.
We typically will use a hole saw and a cordless drill, 2 inches, 3 inches, and we'll take out a plug, okay, at the suspect areas. If we see corrosion, then we start removing insulation, 3-4 feet at a time. Leave it open so the owner-operator can see it. And we'll do that again. Pipes that change temperature, etc. If the insulation's saturated and it's wet, it's dripping, you probably have corrosion. If you see rust, you probably have corrosion on the outside from it staining. If the pipe's frozen in cold facilities and it's a block of ice, there's probably no corrosion because the air can't get to it. Okay, there may be some light surface rust, but that's about it. Usually, when we get more than 330 seconds of a pit that deep, we tell them to start budgeting for replacement within the next 3 to 5 years. Yeah, and then it's critical that when they put the insulation back on, and you can see here, they have to coat the pipe with a good coating, like an epoxy, a ceramic, or an oil base, before they put the insulation on. And they should use 2 layers and overlap the seams, because these come in half pieces. They're about 3-4 feet long. And then use a vapor barrier. It's just like saran wrap, like you use on your food at home. It's just thicker. Once the water gets in there and the air gets in there, that's when you have the corrosion.
But by doing this also,
Repair it.
well,
Yeah, I've been in plants where they've had mechanical integrity inspection. There's holes all over the place like that. And they haven't repaired them, so now we got corrosion going on where they took the plug out.
Accelerating it.
first 5 years, man, after that,
Every year they should be random inspections, and then a thorough one every 5. Very good. Yep, exactly.
And your pressure vessels every 5 years, checking them as well. Any more questions? Good? Everybody good?
What's been your biggest challenge?
What's been my biggest challenge in mechanical integrity?
Yeah.
Is getting the plants to take ownership. We come in every 5 years, and we usually take a couple, if we can get them, techs and put them in our back pocket and try to teach them the same things, because they should be doing the same thing every year. At minimum, the Bulletin 109 forms should be done every year, or a similar type of inspection, whatever the manufacturer's recommend is. They don't read the instruction manuals. They don't get out the manufacturer's manual. They don't follow the guidelines and the industry standard or the manufacturer's standard, yeah. Most common problems we find, piping and valves, insulation problems.
Any other ones? Going once, going twice? Thank you so much. Oh, okay, we got 2.
What type of a filter would you recommend putting on those machines you talked about, the dust?
There's different ones. We'll do it 2 ways. If we're bringing in outside air, we'll put filtration on the walls, on the intakes, and you can get a washable mat from Granger's. It's blue. It's a fiberglass like netting, and they can just take it off. It's reusable. Let's be green. It's recyclable. Wash it, put it back on.
You got a question in the back again, ma'am?
I had a question, just a comment. You were talking about some of the IIAR bulletins that are, to your liking or whatever.
And I'm just one person.
No, I know, I'm just
Okay.
as an inspector, what
Yeah.
I do is go back to your RFP, your written program.
Yes.
So that just needs to, the documentation the facility has, what I'm looking for is that it
IIAR manufacturers.
Not necessarily IR, what is in the RFP.
Okay.
That's the enforcement.
Well, he said as Don said, what's one of my biggest challenges is that they actually have a working CalArt program, RMP. If it says you're going to sweep the engine room floor 10 times a day, you better have documentation and proof that you swept it 10 times a day. They don't follow their own program. Most of the guys have never even looked at the program. As an inspector, you know what the first thing I did is when I got their binder? I opened up, I looked for grease and dirt on the pages. If I don't see any, the maintenance guys haven't touched it. And they're the guys that are supposed to be reading it. Yeah.
Yeah, as the saying goes, they need to be a living, breathing binder, not a dust collector.
And one you look for certification too, a lot of times I'll have a document prepared for, it'll sit on the shelf unsigned.
Yeah.
But I also totally appreciate you saying checking the safety, driving that home.
Yeah.
Yeah, absolutely.
Yeah, it's very rarely done. Sometimes it's done, they don't document. It's like through the course of the year, through the course of the year, they might have a problem with a piece of equipment and a safety trips something out. You've tested that safety. Document it. It's that simple. Yeah.
Any comments or questions?
Have a good conference.
Thank you.